Yeah. Yeah. Yeah, it could. I think I just want to get it. Wait, look at this. The game. This card, bro. That's all I was. Basically. The gym was I got a. That's probably I'll make some random color. I go. Oh, you need to. Oh. Yeah. I don't.
Okay. Any questions before we get started today? So today we're going to finish chapter 14. And there's only one thing remains for the titration, which is actually the indicator. Okay. But I want to actually say the same thing over and over again. To do well in midterm 2, the things you need to do really well is that every time you see a question, so you know what kind of solution that you're going to have. Okay. So we're going to do a few practice today. I don't want to actually solve the numbers. All I want to do is actually make a judgment what kind of solution that you have. Okay, so read the questions and tell me what kind of solution that you're going to have.
That's an acid. That's a bait. Examine this again.
Okay, what kind of solution do you have? What's the solution? What's the solution that, the question is asking which species?
Sodium acetate.
Sodium acetate. That's your solution. Okay. Sodium, everybody follow this? Sodium acetate is actually your solution, right? CH3CONA is your solution. Okay, that is your solution, nothing else. That's the only species. Okay. So is it a weak acid, weak base, or buffer? Exactly, many of you say buffer, right? But it's not buffer. So what is it? Weak base. How do you know? Okay, so inside the question, okay, everybody can see, right? Majority actually select B, which is weak acid, right? And that is wrong. That is wrong. If you select weak acid, you are cooked. Completely. I mean, you have no chance. Right? I'm very serious about these things because you should. If you can actually know what solution you have, you don't know how to calculate it. Okay? So how do you know it's weak phase? Okay, we do this practice because I want you to see. I keep asking what kind of solution that you have, and what is the species that was specified inside the questions, right? So that's where you get started. Okay, and you see that the things you have is CH3COONA, not COOH, right? You need to know what you have. Then you're looking for clues inside your questions because you see it provide you the Ka for a CH3COOH. That is not what you have inside the question, right? The species you have inside your solution is CH3COONA. Okay. Since they are different, they cannot be a weak acid. Does that make sense for everybody? Okay. So since it cannot be a weak acid, but they look so alike, what it tells you is that the species you're actually looking at is a conjugated base of the weak acid. Therefore, you should have no doubt to say the solution that you have will be a weak base. Is that clear? I want everybody in this room to know how to actually determine what kind of solution you have, even if you do any calculations. Okay? Because that's always the first step. Once you know you have weak base, then you will know you should start from OH minus equal to square root of weak base concentration times your Kb. Right? And then you can compute your Kb from Kw divided by your Ka. And then you get your answer. You get your OH minus, then you calculate your POH, then you get your pH. Okay, so that's actually how you should do it. Any questions so far? It's actually so important that, I just can't let go. I want to make sure that you know this. All right? Are you fine with this? Let's try another one. This may be actually let me see if I have another one before you do it, okay? So this is probably one of the most simplest question I can see to determine what kind of solution that you have. Okay, so if you read these questions, right, it says, what's the species that you actually, what's the species that you have for your solution? So what's the species? That's the amine, right? So that's the species that you have. Okay. And inside this question, it already tells you it's actually a weak base. Right? So if it doesn't say it's a weak base, can you tell it is actually a weak base? Now, you actually have a Kb specific for exactly the same molecule, right? So that's actually all the clues that you can have. Okay. If you look at Kb for a species, okay, then you know that species has to be a weak base. Then actually check the species inside your question. If they have the same, then okay, right, it's actually easy. But if they're actually different, then the species will be the conjugated partner of the species with the Ka or Kb. Okay, so it's very important that you see what kind of solution that you have. Okay. All right, let's look at this. This is actually more complicated now. Okay, so this is actually, we're entering chapter 14, right? The first two questions is actually the chapter 13 question. Now enter chapter 14. Okay. Okay, so the answer is a buffer. Okay, so how do you know it's actually a buffer? Before actually can answer that question, first thing is actually that you need to know what's your item, what's your analyte, right? So what's your item? Sodium hydroxide. Okay, so we must know that the titrate can only be strong acid or strong base, right? So here you have two species. One is actually weak acid, here is strong base, right? Therefore, you know the strong base must be your titrate. And your analyte will be the KHP, right? A weak acid. Okay. So after that, I need to actually decide which zone I'm at, right? So to know the zone, what do? You first calculate your equivalence point. Okay, so the way you do it is concentration of your titrate times your BEP should equal to a concentration of your analyte times the volume of your analyte, right? So if you look at the analyte, all right, on this, okay. So the analyte is actually your KHP, right? Concentration is actually 0.057, volume is around 110. Okay. Concentration of your titrate is about half of the concentration, right? That means in order to actually reach the BEP, you need to roughly double amount, okay, double the volume of your analyte. They will make it around 220. Okay. But right now, we have 20 mil, meaning that the titrate is way less than your analyte. Right? Everybody follow the thing so far? Okay. So once you have that situation, all your titrate will be killed. Right? It's going to consume with your weak acid and then produce the conjugated base of your weak acid. Therefore, you have your weak acid with base coexist inside the solution. Then you have a buffer. Okay, so that's actually the basic logical thinking. Okay, if you can quickly see the things I just went through, you are in good hands, okay? Okay, so I guess everybody can see, right? We have two party problem now. Okay, one party like strong acid solution, the other one like buffer. Okay, so let's look at the species that we have inside the question. Okay, what is HNO3? A strong acid. Good. What is the other one? NaOH. A strong base. Okay, you have a strong acid, strong base condition, right? When are you going to have a buffer? Okay, you must have what? A conjugated acid and base, right? And what's going to have conjugated acid and base? It has to be weak acid or weak base.
No.
Okay, meaning that if you have understanding of the definition of buffer, okay, you shouldn't choose buffer as your answer for these questions. Okay, but I guess right now everyone can see if I don't typically mention these things and point that the things you have is really just strong as a strong base. Half of our class is going to start buffer. Okay, so you need to know what species that you have inside your solution. Okay, so here, if you look at these things, the concentration of your strong acid is 0.2, base is 0.1, roughly. Okay, volume-wise, you have more acid than base, right? So from just very qualitative analysis, you should see that the amount of strong acid outweighs the amount of strong base, right? So they're going to interact and kill each other. And we should see that the survivor will be your strong acid. Therefore, you still have a strong acid solution. Just the concentration of the strong acid will be reduced by the strong base, right? So you actually calculate the strong acid concentration, so you can calculate the photon concentration, therefore the pH. Okay, so the example we show today just to show you that the things that you get student a lot of trouble is that you don't know what you have. Okay, in chapter 13 we practice a lot. We give you 9 equations, right? How to calculate pH of 5 different solutions. Strong acid, strong base, weak acid, base, and buffer. You only have 5 solutions. Right? But when you do your titrations, you have 4 zones. And the identity of your solution changes. Therefore, we got complete loss. Okay. But in order to actually get a good score for your midterm 2, that's the things. That's these things that you need to become a master. All right. So this is a very, very important concept. Okay. I hope that today, after all this practice, you have a better idea. Of course, we will keep doing this next week. Okay. So that every time you see a questions, you can immediately tell me what kind of solution that you're going to have. Okay. Let's go. What we're going to do today is actually we talk about, I guess some of you start to do this titration experiment in Jenkins now, this week. Okay, so you must actually heard this term called the indicator, right? So indicator is actually the dyes that change colors when they see a change in pH. Okay, so there are all different kind of indicators. And then here we list out the most commonly used one. Okay, and these are the 6 you're going to hopefully see in your midterm. Okay, so the way you can actually use these 6 different indicators actually going to be determined by what kind of analyte that you're going to have. Okay. So if you have a weak base as your analyte, okay, and then when you reach Let's start from the simple one. This is strong acid, strong base. Okay, let's start from this one. Okay. If you have strong acid or strong base as your analyte, when you reach your equivalence point, okay, we know the pH is going to become 7, right? Because all you produce is just water, okay? So the required indicator for lab, they must be sensitive to the pH change at that range. Okay, so here I actually list out the pH change range, right? And then 7 is actually the things we are looking for. So it must actually fall within the range of your indicator. Okay, so these are the two most commonly used indicators when your analyte is a strong acid or strong base, right? So these two indicator is both thymo blue and then the phenol red. Okay, and then I use this abbreviation to actually remember the indicators for specific analyte, right? So if you have ever watched the conceptual YouTube video that I recorded, okay, so the way I memorize this is actually I use this so-called sleeping baby is treated, right? SBE, sleeping baby is treated beyond. Okay, so I can memorize what indicators that I actually choose when I have my analyte is a strong acid or strong base. Okay. And if today what you have is actually a weak acid, okay, but when you reach your equivalence point, all this weak acid will be consumed, okay, and it will all convert it into its conjugated base, right? Therefore, at equivalence point, the pH is going to be 8 to 10 or 8 to 12, okay, depending on the specific system at the time. Okay, and the indicator that typically people use is phenolphthalein or the alizarin yellow. Okay, so these are the two. Okay, so the way I memorize it is APOPay, right? APPAY. Okay, and if today what you have is a weak base, then you know at equivalence point, all this base will be converted into its conjugated acid. Therefore, the pH range show in the below 7 range, right? And the two commonly used one is your methyl orange and the methyl red. Okay, so those are the things that it's easy if I can memorize it. If you know what your analyte is, then you know what kind of indicator you should get. Okay, so the question I want to go through quickly today is the very last one. Okay, it says which indicator would be the best to use for a titration between 0.3 N NH4Cl and 0.3 N KOH. Okay, so when I see these questions, right, first you need to actually you need to ask yourself, who is the titrant, who is the analyte? Titrant will be KOH, right, the strong base. That means your analyte will be a weak acid, right, NH4Cl. Okay. So this is actually the titrant that will be your analyte, right? So since you know your analyte is a weak acid, right? Then APOPay, right? So APPAY, either PP or AY. Then you will realize there's actually an answer in AY. You can probably actually choose it, okay? But if you look at these two, both of them is actually all within the base range, right? Because all your weak acid will be fully consumed and produce the conjugated base. Okay. Therefore, it seems like both D and E are reasonable answers, right? So under this case, what do you do? The way you do is actually to calculate pH at the equivalence point. Okay. So previously I say if you have a weak acid, typically I use HA to represent it, right? Strong base, we use OH minus to represent it. And then this is going to produce H2O plus A minus, right? And then if you look at the question carefully, you know the concentration is 0.3 m, 0.3 m for both your titrant and analyte, right? So when you reach equivalence point, that means that you're going to have the same volume of your titrant and analyte. Okay. So what it means is actually when these two kill each other, okay. Let's say you have volume one, that's how much more of titrant and analyte that you have. And they are going to consume each other, right? So you're going to do this. Okay, and then you're going to produce that much more of A minus. Therefore, you know the mole of your A minus will be 0.3 times your VT, right? Therefore, the concentration will be 0.3 times VT divided by, right now the V total will be quite much. Therefore, you know the concentration of your base will be 0.3 divided by 2, which is 0.15. That means actually your conjugation at the equivalence point has a concentration of 0.15. Therefore, we can calculate the OH minus concentration equals the square root of weak base concentration times its Kb, which was given here, 1.8 times 10 to the negative 5. So if you do that calculation, you can get your OH minus concentration is 1.64 times 10 to the negative 3. Therefore, your POH, which is negative log of 1.64 times 10 to the negative 3, going to give you a value of 2.79. Therefore, your pH is going to equals to 14 minus 2.79, which is 11.2. Right? So once you know the pH at equivalence point is 11.2, then you can come back and check. If only fall within your answer B, right? So that's actually how you can make the judgment, the absolute correct judgment, okay, which indicators that you can use. All right. So recap of these questions. Okay, so I provide some of the simple rules for you to actually guess which is actually the most reasonable indicator, right? Sometimes you are going to see a question like this. Yes, the one I give you still seems reasonable, but there's actually also another choice, which shows E in this case, seems also okay too, right? So 100% to ensure what kind of indicator you should use, then you will actually calculate the pH of your final solution. Okay, And then once you find out your final pH, then pick the one that fall within the range. The indicator is going to change its color. Okay, so that's all for chapter 14. Okay, any questions so far? Okay, if not, then let's go to chapter 15. Yes. Yeah, go ahead. Yeah, which part? Yes, 0.3 divided by 2. Because at equivalence point, because your titrant and analyte have the same concentration, right? At BEP, what it means actually the mole of your titrant analyte will be the same. Since your concentration is the same, then the volume of your titrant analyte will be the same. Okay, that means actually your final solution will double in size. That's why you get this 2 BT at the bottom. Does that make sense? Okay. It's interesting. It doesn't actually show my printout here. Does anyone ask us to do this? Okay, so I guess I will just actually write it down myself. Okay, so chapter 15 is all about the insoluble salt. Okay, and then the main thing, what you are going to do is actually to calculate the solubility of the salt. Okay, for example, make sure here. So I will just go and give you examples. Okay, so AgCl is actually one of the most well-known insoluble salts. Okay, so if we want to know the solubility, okay, when we talk about solubility, what is the solubility of the salt? Okay, not the solubility of this guy or that guy. Okay, it's the solubility of lead in soluble salts. Okay, so let's say there's actually only certain amount of this salt will be soluble. Okay, so in this case, you can say the solubility will be S for your Ag plus, S for your Cl minus. And then for this insoluble salt, this guy is pure solid. Therefore, when you write out your equilibrium constant equation, it will only contain your Ag plus times your Cl minus. Okay, and in this case, it's very simple. If you know the solubility, it will be just S times S equals to S squared. Okay, so this is actually a simple conditions for insoluble salt. Okay, the things that's going to get interesting, okay, when I say interesting, it means that this actual part are going to be tested. Is that if today I give you another salt, insoluble salt, let's say Ag2CrO7. Yes. Okay, so this is actually an insoluble salt as well. But once it dissociates, it's going to give you 2 silver plus 1 CrO7 2 minus. Okay. When you write out your equilibrium constant of this dissociation process of this insoluble salt, it will be Ag plus the second power times your CrO7 2 minus to the first power, right? If I say the solubility of your insoluble salt is S, okay, then the concentration of your Ag plus will be what? It will be 2S. Okay, that means actually if you dissolve 1 Ag2CrO7, you are going to produce 2 Ag plus. Okay, so if the solubility is actually S, then your equivalent Ag plus will be 2S. Okay, so you need to write 2S raised to a second power times what's the things you are going to have for your CRs? 2O7 2 minus. It will be 1, right? Because right now the coefficient ratio is if you dissolve 1, you produce 1. If you dissolve S, then you produce S. Okay, therefore the solubility will equals to 4S cubed. Okay, so this is actually a part that you will be tested. Okay. And one thing that you need to be very, very careful is that for this type of question, when you do all these calculations, you must use molar solubility, meaning that you must use molarity, right? Meaning moles per liter to put into your solubility. Okay. The reason I say this is because very often when you do your midterms, it will give you a term called the grain solubility. Typically, it has a unit of gram per milliliters. Okay, so many students will actually use that term to do the calculations. Therefore, you'll never get the correct answer. So you must use the molar solubility to do all this calculation. All right. Any questions so far? No? Okay. So just let you know, chapter 15 is actually very, very simple. Okay, calculation-wise, it's very straightforward. This is pretty much the part you need to be very careful. That's pretty much it. Okay, so let's do some questions. What's going on today? Okay. Question number 1. The solubility of silver dichromate at a given temperature is 5 grams per 100 milliliters. Calculate the KSP at this temperature. Okay. After you get your KSP, take the log of that to calculate PKSP. So, what's the keyword? The keyword for chapter 15 is super simple. KSP. Every time you see the keyword KSP is chapter 15 question. Okay. And then if you read the question carefully, right? So what's our cue? What are the things we want to solve? The KSP, right? Which is negative log of your KSP. Okay. Now, let's see what we have so far, right? The data tells you the species that you have is silver dichromate, which means is Ag2Cr dichromate, Cr2O7. Okay. So I believe, okay, the question I have here is actually kind of old already, right? But I believe Chem2 actually change these things. If it's actually a chemical formula, you will actually always give, if it just give you the name in the past, right now, I think it will always give you the chemical formula. Okay, so this species, student used need to translate to this yourself. I think that's not a case anymore. Okay, so you'll be able to get this. Okay. But the things that you should know to solve this problem is that you should know that it will dissociate into 2 Ag plus and then CrO7 2 minus. Okay, so you will need to actually write out this equation yourself. Okay. So anybody have a question for this dissociation process? Everybody know how to write this? So how do we write these things? So the first thing to do is actually you have to recognize a few. Yes. Of the R2, yes. Okay. So how do we actually know we actually write it this way? Right? Because this is actually the part that many students have problems. Okay. This is the time that you should actually use your PR table. Okay. So there are 2 things you pay attention to. One is the superscript, the charges. Okay. So you should know that silver, once it dissociates, carries positive charge. Okay. The other one is like the subscript, how many? Okay, so when I say how many is, pay attention to this. This is actually tells you how many elements was within that chemical formula. Okay, and that's actually how you get this 2 right here, right? Yeah, so there are certain species that you should know the charges. For example, it's actually elements in your 1A group, you will always be positive 1, right? 2A group will always be positive 2. Okay. NX4 plus will always be positive 1. Okay, so let me write all things down because you need to actually memorize this. So you can actually write these things without any problem. This is pretty much the positive charge chaos. There is no charges. Nothing to actually memorize. Okay. So when you see these elements show up inside your equation, okay, pay attention to this subscript and also the superscript. Okay, superscript tells you the charges, subscript tells the numbers. Okay. So this is actually for the cations, right? How about anions? They should actually know. The 7A, the halide group, right? Once they dissociate, it carries -1, right? That's the things you must know. Okay. Then the other thing that you should know is that a few polyatom anions. Okay, I'm going to write those things out to you. Memorize those. Will make your life a lot easier. Okay. NO3, 1 minus. SO4, 2 minus, right? I write out these two first is because those are the conjugate base of the strong acid, HNO3 and H2SO4. Right, you should know like the NO3 carries -1 charge, SO4 carries -2. Okay. A few interesting one, CO3, 2 minus. C2O4, 2 minus. CrO4, 2 minus. Cr2O7, 2 minus. Okay, so here I write out 1, 2, 3, 4. 4. I guess I want to make the cut here. Okay, I guess probably everybody's actually fine with 7, 8, next 1, right? Strong acid, conjugate base of strong acid, I guess everybody has some sense already. Okay, so these are the few that is also carries -2 charge, and they always go like that. Okay, so you should know this. Okay, so if you know these things, then if you come back and look at this, you should be able to know when you have Ag, it should be Ag plus once it dissociate. Okay, so it carries +1 here. The subscript tells you what's the coefficient in front of it, right? And then this guy, Cr2O7, we just say Cr2O7 carries -2. So you write these things out, and you know there's actually only a bits unit of that. Therefore, the coefficient in front of it is actually 1. Okay, so this little table will actually help you to actually write out those dissociation correctly. Okay. So once you have these things, right? If you want to actually calculate your KSP, which you know, if the solubility of the salt is S, right? Then once it dissociates, it's going to produce 2S of your Ag plus. and then 1s of your CR2O7 2 minus, right? KSP will simply equals to Ag plus concentration square CR2O7 minus concentration to the first power. Since you know the concentration of your Ag is 2s, so this will be 2s times S for your CR2O7 minus 2 minus. So therefore, you know your KSP will equal to 2s squared. Sorry, it's actually 4s cubed. Okay. So now what you need to do is actually, if you can figure out the molar solubility of your salt, plugging into this equation, then you're going to get your KSP. Take the negative log of that, then you get your answer, right? So you go back and check, then you will see that the solubility is 5 gram per 100 milliliters, right? Can you just plug in the number into the 4s cubed? The answer is no, you cannot do that because every time when you write the solubility for your KSP, it has to be molarity. Okay, so you don't have molarity right now. All you have is actually the grain solubility, meaning you have 5 gram of this insoluble salt can be dissolved in 100 milliliters of water. Okay, so this is actually not what you want. You want to calculate the molarity. Therefore, you need to do the 5 gram divided by the formula weight. Okay, so the formula weight of your insoluble salt, if you do the calculation using your periodic table, it's going to equals to 431.73 gram per mole. Okay, so you divide the mass of your solute by your formula weight. Therefore, you get a mole of your insoluble salt. Okay. Then you divide by the volume of your solution in liters. Okay, therefore you can get a number of 0.0062. Then you can calculate your KSP is going to equal to 4 times 0.0062 to the cube. Okay, sorry, this is not 0.062, yes, 0.116. So 4 times 0.116 is going to give a value of 0.0062. Therefore, your PKSP will equal to negative log of 0.0062. They give you a value of 2.207. Okay. So question-wise is actually not difficult. The important part for chapter 15 is that can you write out like dissociation equation properly, right? You actually know if the solubility of your salt is asked, what will be the solubility of those ionic species? Okay, if you know how to write those things, then you're pretty much set. Okay, and the things you want to be careful is that you cannot use grain solubility. The only solubility you use is molar solubility. Okay, so that's actually the one of the biggest part of chapter 15. Okay, it's actually pretty simple, right? And then the second type of question you're going to encounter in this chapter is it's going to ask you, is the precipitation going to form? I'm going to see a precipitate when it makes 2 soluble salts. So they're going to actually form a insoluble salt afterwards. Okay. So this statement here is always true. If your QSP is larger than your KSP, then precipitate will form. Okay, so we say the QSP is the situation you mix any solutions, right? And then you can always compute your QSP. If your QSP is larger than your KSP, means you have more product than reactant, right? So how do we actually eliminate those products for the insoluble salts? The way you eliminate the product is actually in form of precipitates. Okay, so if you see your QSP larger than KSP, then you are going to see the precipitate. If your QSP is smaller than your KSP, then you will not form the precipitate. Okay, so these are the two true statements. Okay, any other combination of the things is impossible. Okay, so let's see how we should actually apply this knowledge to the question. Okay, but does everybody follow this is why I say if your QSP is larger than your KSP, you are going to form precipitate. Everybody can agree with that statement? So this will be the question you're going to see. Question number 2. He says the KSP of AgCl at 25 degrees C is certain number. Considering a solution has 2 other solutions mixed together, and then give you 5 different statements. Okay. So, question like this. Okay, you have 5 choices, right? Even you don't look at what is actually inside your question, just look at your answer. You'll realize that 3 of them is just to confuse you. Okay, because the statement is very simple. If you Q larger than K, precipitate. Q smaller than K, no precipitate. There's actually only 2 possibilities. Okay, anything else, just to confuse you. Okay, so let's just look at the answer first. Okay. A says Q larger than K, you're going to precipitate. So that's actually an okay statement. Okay. Second one, Q larger than K and precipitation will not form. You know that is actually not correct. Okay, so you can just cross out your B automatically. Okay, and then you look at this choice C, Q smaller than K and a precipitation will not form. Okay, that is fine. D, you say it will form, then you know that's false. Right? At the very end, it says this solution is saturated. Okay, again, it's a statement to confuse you. So even though it gives you 5 choices, there's actually only 2 choices you can actually select. Everybody see that? Okay, so now, once you actually know, okay, answer can only be A or C, right? Then you need to actually recalculate your QSP, right? So when we get back to these questions, how many species was mentioned? 3 species was mentioned, right? The question is always going to have this format. Among the 3, one of them is insoluble salt. The other 2 will be soluble salt. Which one is insoluble salt? How do you know it's AgCl? Because it gives you the KSP. Right? Only insoluble salt will going to give you KSP. Therefore, you know the equation that you're going to write is what? AgCl, solid, dissociate become Ag plus aqueous plus Cl minus aqueous. Right? So once you know this, then you can actually write out your QSP, right? QSP will be what? You see this 1 to 1 to 1, right? So the solubility of Ag plus will be S, CO minus will be S, right? Therefore, the QSP is just S squared. Okay. So now you need to actually figure out what's the concentration of your Ag plus and what's the concentration of your CO minus. Okay. And this concentration of these two species will come in from two other solutions. Okay. Let's look at first solution you have is what? Calcium chloride. What's the concentration of that? 1 times 10 to the negative 7. Right? The things I want to pay attention is that you should know what is actually the ionic species you are looking for. The ionic species must belong to these two, right? Because these are the two that's going to form precipitates. Okay, so in your calcium chloride, it's going to produce which species? Ag plus or Cl minus? Cl minus, right? How much Cl minus can one CaCl2 produce? 2, right? That means actually if you have less concentration of your CaCl2, the Cl minus concentration, because this 2 will make it 2 times 10 to the negative 7. This is a concentration you need to actually use. Is that clear? Okay. So let's actually use first soluble salt, right? Then you look at the second one. You see this guy? AgNO3, right? Which species is going to produce? Ag plus, right? In what ratio? 1 to 1 ratio, right? Because the subscript of your Ag is, it isn't right? Because there's actually only one of it. Therefore, the concentration will simply equals to 1 times 10 to the negative 3. Okay? Therefore, you know the QSP is equals to the solubility of your Ag plus right now is 1 times 10 to the negative 3 times your Cl minus 10 to the negative 7. Therefore, your QSP will equals to 2 times 10 to the negative 10, right? That is your QSP. Once you have your QSP, then you compare to your KSP. Okay, we know the KSP is equals to 1.6 times 10 to the negative 10. Then compare these two, then you know your QSP is larger than your KSP. Therefore, you are going to have precipitate. Therefore, the answer will be A. Okay? So recap this. Every time you see a question like this, it's going to be very symbolic, okay? Because you're going to see 5 questions and start to compare your QSP, KSP, and telling you the precipitate will form or not. Okay. Make sure you know among the 5, only 2 of them is reasonable answer, right? Q larger than K, precipitate. Q smaller than K, no precipitate. These are only 2. Okay. Then what you need to do is actually to identify first who is actually your insoluble salt. Then write out the ionic species that matters. Okay? And then go to the other 2 solutions to see how they are going to contribute to each of ionic species. Pay close attention to the subscript so that you know you can write out the proper concentration first. Once you have that, then you can compute your QSP. Then you can compare that to your KSP, then you will know which answer is actually the right answer. All right? Yes. You know. Yeah. I guess in writing this is a little bit confusing here. Maybe I should just write this. Right? Yeah, this will actually make it more clear. Okay, so this is how you solve this type of questions. Okay, you're going to see a lot of these questions. Okay, yeah, don't be fooled. Okay, make sure you know. Okay, it's just trying to confuse you. Okay, there's only two possible answers. All right, so let's actually question number 2. The third concept that we need to know is this. This is actually pretty interesting. Effect of pH on the solubility. Okay, so the question multiply says, okay, which of following species is going to change its solubility when you put it into a more acidic or more basic solution? Okay, so the way you handle these things is that starting by identifying the anionic species of your insolubles. Okay, so if your anionic species of your insoluble salt is OH minus, okay, then when you actually put this in an acidic solution, because your acid is going to consume your OH minus, therefore the insoluble salt will actually continues to dissolve. Therefore, the solubility is going to increase. Okay. However, if in a basic solution contains of OH, right, the Sharp principle tells you it's not going to allow you to further dissociate. You will actually push back because right now you have so much OH minus inside the solution. Therefore, the solubility of your salt is going to decrease. Okay. So that's actually scenario number 1. Scenario number 2 is that if today you have a conjugated base of a weak acid, which is your A minus, right? So if you put into your acidic solution, your conjugate base will actually interact with the strong acid. Therefore, so your conjugated base will interact with your strong acid. Therefore, the solubility will increase as well. Okay. But if you put it into a basic solution, because your OH minus doesn't really interact with your A minus, so it doesn't have much effect. The other one is actually if you have a conjugated base of a strong acid, for example, the Cl minus, Br minus, I minus, right? Those species is actually neutral. Okay, so regardless you change its pH, it's not going to change the solubility of the salt. Okay, so those are the basic principles that you should actually know. Okay. We're going to go through the questions so you can see these things better. Okay, so let's look at question number 3. Which of the following compound has different solubility with a lower pH? Okay. Lower pH means you actually put it into an environment has a lot of H+. Okay. Keyword here, solubility. Okay. So since you see this keyword solubility and also the pH, then you know it's testing you the effect of pH for the solubility. Then you should know you need to first identify the anionic species inside your salt. Okay. This one will be NO3. This one will be Cl minus. This one will be OH minus. This one will be Cl minus. And this one will be CrO4. 2 minus. Okay? Then you look at this. NO3 minus. NO3 minus is the conjugated base of HNO3, which is a strong acid, right? Therefore, you know its conjugate base will be neutral. Therefore, it doesn't have effects. Okay, so no effects. Okay, second one. Cl minus is the conjugated base of HCl. Again, a strong acid, therefore this one is also neutral. And then no effects. Okay, the third one, OH minus, when you put it into an acidic solution, they're going to concern each other, right? And will push this solubility to the product side. Therefore, you know the solubility is going to increase. Okay. Cl minus, same thing again. It's going to be neutral, therefore no effects. Okay, the very last one, CrO4 2 minus, which we know its conjugated partner will be CrO4 minus. Okay. Apparently, it is a weak acid. Everyone have a problem with that statement? But apparently, it is a weak acid. Okay, because I added proton to it, right? So it should be an acid. Okay. And the reason I know it's weak is because it is not a big 7. So I say, okay, let's actually a weak acid. Therefore, this is actually a conjugated base of a weak acid, right? When you throw in this weak base into a low pH environment, the acid is going to consume your weak base, right? So you actually get into a situation that your weak base keeping consuming, therefore it's going to solute. The solubility is going to increase more, okay? So your solubility will increase as well. Okay. So this is actually the third type of questions that we're going to encounter. Okay. Yeah, I don't think I have enough time for the very last question. We'll do it next Tuesday. Okay. Any questions? Yes. Yeah. Because the KSP is the part of your system. So if you have added the OH method going to become first, but you get but they want to supply that. No, we don't. Because I don't know. Yeah, no, because we don't. No, we don't. No.
I have a question about the small x approximation.
Yes.
I don't fully understand.